Hi, I'm Tim. Join me in this video as I go through RC electronics for newbies, for newcomers to the RC field. I'll give top-level discussions of the transmitter, what it does. I will go over a setup of a typical airborne installation with the batteries, ESCs, motors, how all that interplays. And finally, we'll see how it all works together with this little 6-channel setup to show reversing and just how everything comes together. Let's get to it. So for a typical RC setup, we'll talk about two things: the ground station, which is the transmitter that you hold and control, and then we'll go into the flight pack, what is actually in the airplane. All this is in the airplane. So you'll have to have a transmitter. I'm not getting sponsored for any of this. These are just my personal preferences. I've had a lot of good luck. I enjoy working with Spectrum products. There's a wide range of transmitters out there. What I would recommend, if you're in the market to buy a transmitter, do buy a computer-based transmitter. You can tell by the little screen here. It is worth a little bit of extra money, and also the newer ones work at what they call 2.4 gigahertz, which means you are binded or electronically connected to a specific receiver. I'll discuss that with the setup, and you don't have to worry about getting jammed by somebody else turning on their radio. Also, there have been some huge advances in antennas. I like this short one here, nothing can break off. You'll need an electrical supply for this transmitter. What I do on this one, I just have 4 AA batteries. That's a fairly typical setup. You can get some with rechargeable. I don't mind the AA batteries. Go to Costco, buy a bunch of the AA's. Because there's no motors or moving parts in the transmitter, the batteries last a fairly long time. You can read the voltage on here. I write down here the minimum voltage of 4.3. It just makes things easy to have a few extra batteries in my flight pack. For the controls, this is typically mode 2, what they call. This is up and down for the elevator. Ailerons, bank left and right to include turns. Rudder left and right, and typically throttle. You'll see a bunch of other buttons up here. These are other channels that can be assigned to do specific things. I'll go through that briefly in the video. And it could be lowering the gear, it could be lowering flaps, it could be a bomb drop. It's whatever you want to assign to a servo to do in the airplane. And by the way, if you want to jump ahead or see a specific section, there are chapters in the bottom of this video, also links to the various airplanes and products that I describe in the description. One other item, this is a DX6. It's a 6-channel receiver. I think 6 channels is a good minimum to get. Many of the ARFs that you can buy these days have retractable gear and flaps. You'll need 6 channels to operate that. I think 6 is a good minimum. 4 is an absolute minimum for your flight controls. 4 channels would be your elevator, ailerons, rudder, and throttle. But 6 is a better option if you can get to that level. Let's talk now about the flight pack, all the RC electronics that go into your airplane. This is a fairly typical setup. So what will have happen is you have a battery, and we'll go into more detail on this. The battery is connected to the electronic speed control. The electronic speed control provides electrical power from this battery to the receiver and your servos. This is one servo here. It's very common to have 6 or 8 servos in an airplane. And of course, it's connected to the motor. This is where the prop is connected. This rotates to provide the power to fly the model. This is a fairly new thing to flying. This is a remote ID. It's the Flight Test Easy ID. I think it's a nice little system, and I will discuss that in a little bit more detail. All you do essentially is plug that in. It picks up the GPS signal, and off you go. So let's talk about the receiver first, okay? There's a wide range of receivers. One of the reasons I like the Spectrum systems are Spectrum were the original developers and introduced the 2.4 gigahertz systems. And I think having a Spectrum receiver with a Spectrum transmitter, they just seem to bind and work together better, but it's not a requirement, it's just what I use. This is an AR620 receiver. I bought it off of Amazon, very lightweight receiver. You'll notice that it does not have any external antennas. The antennas are built in. Back in the old days of receivers, this is a pretty common setup with a receiver. You'd have these 2 antennas that had to be orientated completely correctly in the airplane to get your signal. It is a wonderful thing to have an internal antenna. It's just one less thing to go wrong in the installation. This is a bind button to bind it to the transmitter. We'll go into a little bit more detail on that. Also notice here that you'll have various ports. It starts off with BATT, then port number 1, 2, 3, 4, 5, 6. So this is obviously a 6-channel receiver, and you plug in servos, typically servos, the remote ID into these ports. Now, it's important to note the BATT, that is short for battery. For our electrical powered models, we never plug in anything into the battery port. That battery port was back in the older days, or today. If you're flying a gas-powered model, gas-powered models don't have an in-flight battery for the electrical motor because there's no electrical motor. So what you have to do is have a separate in-flight battery to power the electronics, which is the receiver and the servos. That is what you plug into the BAT port. And then channel number 1 is the servo to control the throttle. So for electrical powered models, we just don't use the BAT, but it's there for gas powered models. Now going back to the channels, number 1 for electric powered models is always, I repeat, always connected to your electronic speed control. It is always connected to electronic speed control. And what will happen is, through the magic of everything working, the receiver will receive your throttle indication, communicate to the electronic speed control on how fast the motor is going to turn. Now, the remaining ports are typically, number 2 would be aileron, number 3 is elevator, number 4 is rudder, 5 and 6 are auxiliary channels. Typically, 5 is the gear, and 6 are the flaps. And I'm going to talk about how you can determine what those are and how you can make the assignments. And what happens is, this is one of the inherent advantages of having a computer-based radio. You can assign different actions to the various channels. Let me show you very quickly how to do this. Now, before I do this demonstration on the DX6, I have a very good video. I'll put the link up here of tips and tricks on the DX5. I take a much, much deeper dive of what all the menus and sub-menus mean. On this one, let's just look at how to assign a channel. So let's take a look at figuring out what channels on the receiver are what. So this is my DX6. This is the on-screen. This is the name of the model. I'm just calling it RID for this purpose. Notice the volt is 5.1. My minimum is 4.3, so I'm good to fly. And this is a countdown timer trim. So to get to the menu to look at the channel assign, first of all, this is called the scroll wheel. On the DX6, we press it down and we get a list of functions. Because this is something that we don't do that often, looking at the channels, we do it once when we set everything up. We go to a system setup, we push that one time, we're going to disable the transmission, which is fine. And what we do is we go down to channel assign. We push this one more time, and this shows that number 1 is throttle, number 2 is aileron, 3 elevator, 4 rudder, 5 is gear, and 6 is aux1, like I said. Now, notice up here we have various channels, C, switches D, F, and so forth. What will happen is we go to the list, we go to next, and this shows what switch we could use for the gear, number 5, and aux, number D. So for example, aux is going to be the flaps. We can press that, and we can pick switch F, D, C, and so forth. I have selected D, and that is the switch right here. So that means this will go to port number 6 and work for the flaps, and the same thing works for the gear if you want to do it, just to whatever switch you want to assign. Let's talk a little bit about the batteries. The vast majority of flyers will be using lithium polymer or Lipo batteries. Without going into a lot of detail, there are 2 things about the battery: the number of cells and the capacity. So the nominal voltage for a cell is 3.7 volts. If you see an ARF kit where it says you need 7.2 volts, that's just a 2 cell. 11.1s would be 3 cells. That's what you need. The thing is, the more cells you have, the more energy you go to the motor just simply goes faster. So this is a 2-cell battery. You can see the 2 layers right there. It says 2 cell on the battery. Okay. That is for smaller models. It should provide sufficient power. This is 3 cells, more thrust, and the size, they're both 1350 milliamps, 1350 milliamps. That's just an indication essentially of how long you can fly. So if this was, say, 3000 milliamps, 3 cells, the voltage would be the same for the power of the motor. It could just fly longer with a larger battery. So it's a trade-off. The larger batteries weigh more. They take up more space in the airplane. You're just going to have to make a choice of what one you're going to use. I've got a very good demonstration of the difference between a 2-cell and a 3-cell battery with my F-35 model. I originally flew it with a 2-cell. I was trying to keep the weight down. And you can see I'll show you the launch here next. On the test launch, it just simply didn't have enough power to fly. Just didn't have enough power to fly. I swapped out, put in a 3-cell. The ESC was able to handle that. Now I had a great increase in thrust, and the plane flew flying. So let's take a look at those videos right now. This is the no kidding maiden flight of my F-22 made from foam board with a 2-cell battery, getting full throttle. You could hear it that's where it's going. Pulling up the nose, it just didn't have enough thrust. Put in a 3-cell. Gave it a launch, kept the nose up, and off we go. Plenty of power. Again, this is my first flight with it, sorting it out. As we circle back over the field, very nice flying airplane. And plenty of power with a 3-cell battery. Other thing that's super important with your Lipos, you want to check them with a battery checker before every flight. You can buy them at Amazon. There's just any types of a range of brands. I've got a video link I can put up on this. And it's powered by the battery itself. The battery, this are the 2 wires that go to the electronic speed control. Super, super important, black and red. If you get those mixed up when you connect it, you will short out the ESC. This extension is what we call a balance lead. It is used with the magic of today's chargers to correctly balance the different cells as you charge it. It's just a requirement to safely operate Lipos. But we can use this balancer to also check the power. So you simply plug it into the side, and you can see for each cell the voltage and, more importantly, the percentage of the charge. And this cycles through the 2nd cell, the 3rd cell, the difference in voltage, and so forth. So it's very important to check your batteries before you fly. Make sure you have a full charge. And where this will save you is if the cell goes bad, it'll pop up immediately when you check the voltage. Just don't fly. If a battery's going bad, throw it away, get a new battery. Otherwise, you're risking a crash. When you purchase an ARF, typically the electronic speed control and the batteries are installed. Many of the ARFs, they're quality ARFs. I don't even see the electronic speed control of the batteries deep inside the airplane in the cowling. But the ESC and the motors will work together. What you'll typically have to supply for the majority of ARFs are your own LiPo battery, your own receiver, because they have no idea what transmitter you're using, and then, of course, the transmitter itself to control it. That's fairly typical. If you're building your own airplanes or a kit and you buy an electronic speed control, I just want to let you know that when you buy the speed control, you'll have 3 wires that go to the motor always, 2 wires that go to the battery. As I mentioned, it is absolutely critical to keep the polarity straight between the red and the black. It has to match up with the battery. If you get that backwards, when you attach the connector, it will blow up the electronic speed control. But I want to point out, you're going to have connectors to connect from for the battery, for the motor, and for the battery. So if you look here on the board here, these are what we call bullet connectors. And you'll have to solder those onto both your motor and the electronic speed control. Again, you can get these on Amazon very quickly, your favorite hobby store. And I use XT60 connectors. I like a lot to connect to the battery. You can see the connectors right here. It simply goes in. It's a very good connection, easy to solder, and it's super easy. Again, on Amazon, I got these XT60 connectors. They're already soldered to the wires, so all I have to do, strip off some insulation, connect the wires together, and I'm all set to go. So that's just an FYI. As you get your batteries, you have to add the connectors if you're building your own. Let's talk a little bit about the electronic speed controller. The electronic speed controllers are just a wonderful thing because it makes it so easy to hitch up the electrical power system. But what I want to point out is the electronic speed control, your electronics in the airplane, your receiver and your servos operate on about 5 volts. However, this one's producing about 11.2 volts for the motor. You want more voltage for a faster spinning motor. So what will happen is when you plug all this together, and we'll plug it in at the end here, the electronic speed control does some magic inside to step down the voltage to 5 volts for the receiver and the servo, so those are operating properly, yet keep the full 11 or whatever, 7.2 volts, depending on the cell, to let the motor go, operate. You'll have to look at the specifications of your ESC. This is a Talon 25. It says right on here, I won't show it in the video, it's small print, 6S. It can have up to a 6-cell battery. Just do your research on that. 6 cells is a pretty big battery load for burst currents. But that's what the electronic speed control does. So it's a very nice feature because the battery controls all the electronics as well as the motor. Virtually everybody is going to be using brushless motors these days, and you can tell any motor is brushless. It has 3 wires connecting to it. There are going to be a range of colors on the motor. This one is black, blue, and red. It doesn't matter. There's no polarity with the motor. You simply connect all 3 wires and the motor should work. If the motor is spinning in the wrong direction, it should be clockwise if you're looking at it from the cockpit, counterclockwise, looking at the front of the airplane. If you want to reverse the direction of a brushless motor, you just take any 2 of these wires and just swap the connectors, put them in the other ones. It'll go in the right direction. Let's talk about servos for a second. This is a servo. This is the arm that'll move to operate the control surface. You'll have 1 servo for each control surface, ailerons, elevator, rudder. You may have 2 servos for the ailerons. We'll demonstrate that with the foam board demonstrator. And that's just for ease of installation, but they're connected through a Y cord that'll explain. Now, the important thing about servos, they're essentially a commodity. For sport flying aircraft, you can get them from a wide range of sources. If you have some high-performance competitive airplane, you can get a more expensive one, but they work well. They come in different sizes. You're generally looking at the weight and size for your model. What I do want to point out is this is the connector for the servo. And you can't plug it in backwards. That's the good news, but there is always a darker color, either black or brown. This is what we call the ground, and that has to be typically at the bottom of the receiver. So the black and red on this one are the power. The yellow is what we call the signal. That's the signal of where the servo should be. The important point is when you plug it into the receiver, the ground has to be in the bottom. If you accidentally put it in where the ground is at the top, nothing bad will happen. The servo simply won't work. I've been caught on that several times. Just make sure that when you plug in your servo, that black or brown wire is at the bottom as you plug it in. This is a remote ID module. I got it from Flight Test. I think it's really pretty easy to use. The thing about Flight Test is they've got wonderful instructional videos about how to set this up, how to plug it in, and it truly is an easy thing to do. So remote ID is a new requirement. It became in effect and enforced in March of 2024. There's a range of videos of remote ID. I'll put a few in the description that you should look at. But essentially today, after March of 2024, this is being filmed in July of 2024, if your model is 250 grams or over, that's about 8.8 ounces, and you're flying recreationally, you've got to have a remote ID. Now, the good news is 1 remote ID is sufficient for all your recreational models. If you have 20 RC models, you can swap the remote ID to each one of the models. And all you have to do is plug it in. It'll have a red light as it's searching for the GPS signal. The first time you plug it in, it might take 2 minutes. After that, it's a much shorter time, and then you're done. There's also a little bit of a one-time registration on the FAA's drone website because the FAA has to know the serial number of the remote ID because the purpose of remote ID is to identify the RC pilot to authorities if they want to figure out if a model is lost or violating some airspace. Let me show you very quickly how to log this onto the FAA website for your remote ID. And then each model you have, you just have to put in a descriptor so that the authorities, if they find your model, can match up the model with the remote ID. So let's take a quick look at that. It can be hard to remember the website. I just Googled register remote ID. It takes you to the FAA page. It talks about remote ID, compliant registration, and recreational flyers. We're going to be doing a recreational flyer. So we go to the FAA drone zone, this link here. This will take you to the specific page needed to register your drone and add things like remote ID. This is the page after I've logged on. The devices are the number of airplanes, and that's me. And here is the add a device page, just with the device type, remote broadcast ID, a nickname for it. And finally, once it is added to the page, you can see it on my inventory sheet. I mentioned earlier the concept of binding your transmitter to the receiver. Once the transmitter and receiver are bonded together, they know each other. So when you turn on the transmitter and the receiver, that's the only receiver it looks for. It is just a breakthrough technology inherent to 2.4 gigahertz. What it means is you can fly, you're never going to be interfered with, etc. But you have to bind at the beginning. In the past, that was a little bit tricky. It's a lot easier now, at least with the Spectrum ones. Normally, we turn on the transmitter first, but for binding, I'm going to turn on the flight pack. I'm going to put it into the bind mode by pressing this button. You'll see a very rapidly flashing light. To do the one-time bind, there is a bind button up here. We hold that down while we turn on the transmitter. You can hear the transmitter look for it, say it's binding, and then it's binded. So let's do that right now. So what I'm going to do is plug in the system. And remember, with these XT60s, there's only one way to plug it in. And what we're going to do is we're going to put this into the bind mode. I just hold down that button. See that flashing light? I'm going to hold down the bind button on the transmitter. One time I turn on the radio.
Binding. DSMX 22 milliseconds. Telemetry. Bind complete.
That's all you have to do. The light comes on steady, and now that's how it works. So this would be the elevator, and that's everything's working, and the motor will just touch the throttle. See how that spins around right there? There's no prop on it, obviously. And then you can plug in your other servo. So everything's working. Electronic speed control, the servo. So let me plug in the remote ID. I'll come back when it's locked on. You can see the green light. So I've just plugged in the remote ID. You can see the red light. It's looking for the GPS signals. This is absolutely normal. And we'll come back in a second when we get the green light. So we plugged in the remote ID. It's getting a little bit of time to get the GPS signal. That's the red. I want to cover a couple other things. Sometimes you might want to extend the wires for your servos. It could be further along. You just need to extend it. There's no problem extending these wires. And what you can do is you can buy wire extensions and just plug in on either end for your servos, so you can extend them. It's no problem doing that. You can get shorter ones, longer ones. I just buy them at Amazon. The other important thing I want to point out is extending the wires for the motor and the electronic speed control. You may have a situation where the motor's in a pylon or it's in some remote location. For a bunch of technical reasons, the way it works is you cannot, or you have to be extremely careful extending the battery wires. They have a specific length because the battery wires are speaking from the ESC to the battery. It has to see a known length. Otherwise, the signals can kind of confuse each other as they go back and forth. There is not that restriction to the wires to the motor. There's no communication. That's already done from the ESC. I've had extensions up to 12 inches. It seems to be okay, but you really should not extend the batteries of the wires. You have to add capacitors and do a bunch of stuff for that. And we have a green light on the remote ID. Again, I think that's pretty impressive. I'm in the basement of my house and managed to pick up and lock onto the GPS signal. When you're at the field, you should have no problem with the lock on the remote ID. So let's take a look at a typical installation with 4 channels of control in the flaps. This is the motor here. Just for safety, I have this little wood thing for the prop. You don't ever want to have a prop on here because you could hurt yourself. The motor is installed. The 3 wires come up here with their connectors. These are the flaps. Each one has a flap servo. Ailerons on the left, ailerons on the right. This is the rudder servo, and this is the elevator servo. And you can see the connecting rods that go back here. This is a pretty normal connector for the servos, for the controls. Again, I got these from Dubro on Amazon, just easy connectors. They're quite easy to install the servo arm, and you have a screw, either an Allen head or a flat head, to put in some music wire. You can slide it back and forth, screw it down, it's in place. This is a Z-bend to the control rods. The Z-bends, I want to take a moment just to show you how to do a Z-bend, and it's really quite easy. This is some music wire, and to get a good Z-bend, get a good set of pliers. We put them at the top, and what we do is we just bend the wire a little over 90 degrees, so we have that right here. The trick is we put it in sideways, and we bend the wire straight down like this. So we have this, and now we put this on the top, and we simply bend it over like this, and you get, with a little bit of practice, pretty reasonable Z-bends by doing that sideways technique. And then what happens with the Z-bends is just a very secure connection into your control horn. Now, the other thing I want to point out before we hook this up with a receiver is you'll see that we have, in this case, the wires for the ailerons on the left and right. How do we get that to the receiver? What we do is we have what's called a Y connector, where you have the single connector that goes into the receiver, splicing together, and you have two connectors where you can connect your left and right servos onto that. This is very common to be used. That way one port can control two servos. Again, I bought these from Amazon, and you just plug them in. So I'm going to use a Y connector for both the ailerons and the flaps, connect it into the receiver, and then we'll be good to go. So give me a second to hook all that up. We'll demonstrate everything in this model, then we'll be done with the demonstration. So I've hooked everything up to our iron bird, as they say in the aerospace industry. You can see that it's just a complicated network of wires with the Y connectors to the ailerons, the flaps. You've got the remote ID still looking for a signal here, so you have to plug in it again. But what happens is, it's very important when you build an R for your own airplanes to connect all these things, the connectors, make sure all the servos work outside the airplane before you install them. And what is very common is you can just simply label, like for here, this is an R for the right aileron, to keep track of what is what. It is important to make sure you understand in your mind where the wires are, where they go before you install them into the airplane, because you can get lost with it. The other thing that can make it even more complicated is a lot of RFs are including navigation and position lights on the plane. These lights are typically just two wires, because all they need is power. They don't need a signal, but the lights can go into any open receiver any port in the receiver, to include a Y connector if you're up to 6 receivers. Again, this is another advantage to having the 6-channel radio. You can see we don't use the bat because it's electrical. This number 1 goes electronic speed control. This is a Y connector to the ailerons, elevator, rudder, the remote ID, and then a Y connector to the flaps. So everything's on here. Let's take a look to see how that works. So this is the elevator, which is back here. That's up and down. The rudder on the back is typically over here. These are the ailerons with a Y connector to each servo. So that looks like that. And notice that you have to orientate where the control arms are, if they're front or back, to make sure that everything works for your installation. And then with the channel assigned, remember for the flaps, we put that to channel D right here. So this is down, full down, and then the flaps are up like that. And then of course the throttle, make sure nobody's going to get hurt. And again, if you've got to reverse the motor, you just swap any 2 wires and the motor will go in the correct direction. And then the remote ID is still looking for its signal. So that is an overview of RC electronics, the transmitter, the flight pack, batteries, extending wires, remote ID, testing everything before you install it. That's all there is to it. So good luck with your installations, and thank you for watching the video.
Greetings from Hilltop Live.